Good afternoon. So we're going to continue our discussion about atomicity and how to achieve atomicity. And today the focus is going to be on implementing this idea called recoverability, which we described and defined the last time. So if you recall from last time, the idea is that when you have modules that interact with one another, and in this example, M1 calls M2, and M2 fails somewhere in the middle of this invocation, and it recovers, the goal here is to try to make sure that the invoker of this module, in this case M1, or all subsequent invokers of M1, don't see any partial results that were computed during this execution when M2 failed. And this was this idea that we called recoverability, where, and the definition of recoverability was that an action which is made up of a composite sequence of steps is recoverable from the point of view of its invoker if it looks to the invoker and to all subsequent invokers as if this action either completely occurred, or if it didn't completely occur and aborted, it aborted in such a way that all partial effects of that action were undone or backed out. So in other words, recoverability is this idea that you either do it all, either complete the action, or do none of the action, that the effects are as if you were able to back out of the action. And we use this idea to then talk about a particular special case of recoverability to implement a recoverable sector, which is a single sector of a disk where what we were able to do was to ensure that everybody reading, we defined a put procedure and a get procedure, so readers would invoke get, and we ensured that everybody doing a get would never see the partial results of any put. So if a failure were to happen in the middle of a put, people doing a get wouldn't see these partial results. And the main idea here was to actually maintain what is more generally known as a shadow version or a shadow copy or a shadow object of the data. And we maintained two versions of the data that we call D0 and D1. And we maintained a sector that we call the chooser sector to choose between the two shadows. And what we were able to argue was that the chooser always points to the version that you want people to get from, to read from. And so when someone does a put, the idea is first to write to the version that's not currently being read from. So if the chooser points to 0, then the putter would write data into 1. And if a failure happened in the middle of that write, there's no problem because people who read would still read from 0. And we reduced this case of proving this algorithm correct to the case when a failure happened in the middle of writing the chooser sector. And we were able to argue that as long as people, if a failure happened in the middle of writing here, either of these versions is correct because a failure by definition didn't happen in the middle of writing either of these two sectors. And therefore, you could pick either of them and read from it. And during this process, we came up with this notion, which we're going to generalize today, called a commit point. The commit point is the point at which, for any action, the results are visible to subsequent actions. And if a failure happens before the commit point, then the idea is, in general, you would not want people not to see the partial results that might have accumulated before the failure occurred. And in this particular case, the commit point is when the chooser sector gets written to the current version of the data, and that call to writing the chooser sector returns. And if it returns, then you know that people doing a get will get from the version that just got written. So in the implementation of recoverable put, the commit point was when this call returned. So now the question for today is how we deal with larger actions. Because this is a plan that works pretty well for single sector puts and gets. So we were able to make individual sector reads and writes recoverable. But if you think about any serious application or even any toy application, in most cases, you end up having more data than what fits into one single sector. And you might have things touching data all over the place. And our approach toward doing this is to actually first define what a programmer must do, what somebody wishing to write a program that is a recoverable action must do, and then we're going to implement that underneath in a system, so the programmer doesn't have to worry about implementing recoverability. So the idea here is for the programmer of a recoverable action to start writing that action using a system call, a call that we'll call begin recoverable action, and then discipline herself or himself to write some software which has a small number of rules as to what goes in, what can go in here. And then explicitly when they want to commit that recoverable action, make its results visible to subsequent actions, invoke commit. And then they're allowed to do a little bit more work or a lot of work here, but there's very strict restrictions on what they can do after a commit. And then they can end using end recoverable action. And this phase here before the commit is called the pre-commit phase. This is the post-commit phase. And the idea here is if a failure occurred here or an abort occurred before the commit, then and this action was made to abort, then the system must restore the state of all of the variables and all of the data that was touched here to the same state before this action even got invoked. Okay, it's as if none of this happened. So this is the not at all part of this definition of recoverability. And once you reach this point at the commit returns, the only thing you're allowed to do here are things that cause you to complete. You're not allowed to abort here. You're not allowed to back out here. So this, once you reach this point, it means the action you're in the do it all part of do it all or not at all. So you have to complete all the way to the end. And what this really means is that all of the data that you want to manipulate and all of the resources that you want to accumulate, and we'll look at locks as a resource that you would like to accumulate in order to enforce isolation, which is a topic for next time. All of that has to happen here. So that once you reach this point and it ends, then even if a failure occurs when it restarts, you just have to crunch through and finish what was going on here, and that can just happen. There's nothing to acquire, no resources to get. All of the data variables have already been put in their correct situation, in their correct state. So the interesting part really is what happens between begin recoverable action and until the commit finishes, and that's what we're really going to focus on. Now, in addition to commit, there is another call that we have to explicitly think about, and that's abort. And there's 2 or 3 different ways in which abort may be invoked. The first is a programmer might herself or himself have abort in their code. For example, in that bank transfer application, if you discover that your savings account doesn't have enough funds to cover a transfer, you read it and then you maybe write something and then you discover that you don't have the funds to cover the transfer, you might just abort. And the semantics of abort are that once abort is called by the programmer, they can be guaranteed that when the next person invokes a recoverable action that involves those same data items, those readers will see the same state as if this action never started. So what this means is that the system must have a plan of undoing and backing out of any changes that might have occurred before this abort is called. Another reason an abort might occur is that you're for example, a database application and you're booking all sorts of things like plane tickets and air tickets and hotel reservations and so on. And you book a few of them and then you discover you can't get one of the reservations that you want. You might, as a user, might abort the whole transaction. And that causes all of the individual things that were in partial state to abort. Another reason why abort might happen is that, and we'll see this the next time when we talk about locking, anytime you have locks, we already saw that anytime you have locks, you have the danger of deadlock. And one way in which the system implementing these atomic actions, both for isolation in particular, deals with deadlocks is when 2 or more actions are waiting for each other, waiting on locks that the others hold, you just abort one of them or abort as many of them as needed for progress to happen. So the system might unilaterally decide to abort certain actions. And what that means is that the system's abort had better have a plan to undo all partial changes that might have occurred before it returns from abort. Okay, so that's the general model. So what we're going to do today is to understand what happens when data variables are written inside one of these recoverable actions, how commit is implemented and how abort is implemented. And that's the plan. And once we do that, we will have implemented recoverability. So we're going to study 2 solutions to this problem. And the first solution uses an idea called version histories. And version histories really builds on an idea that we did see the last time when we talked about recoverable sector, which is this rule that we call the golden rule of recoverability, which says never modify the only copy. Because if you modify the only copy of something and a failure occurs, then you don't really have a way of backing it out because you don't know what the original value was. Version histories generalize that idea to say never modify anything. So the idea is anytime you want to write a variable, you don't actually overwrite anything. You create another version of the variable and somehow arrange for a set of pointers that point to, for a variable to point to all of the versions of any given variable. And to understand that, we need to understand the difference between conventional storage, like a conventional variable that also called a cell store or a cell storage item, and a variable that allows you to implement versions, which we're going to call a journal version, a journal-based storage. So cell storage is traditional storage. So if you have a variable x that's cell storage, and you set x to some value v, what ends up happening is that the cell that contains x is, you write the value v into x. In other words, you overwrite whatever there is, as you know, and replace it with v. And this overwriting really is what causes the problem. If you don't have another copy of this variable somehow maintained, overwriting means that this rule of recoverability is being violated. We're going to use the word install for these writes. So we'll be installing items into cell stores. So what that means is assigning a value to a cell store variable. And the problem is this gets in the way of this golden rule. So what we're going to do is use these cell storage items that we know how to build, that's the memory abstraction, to build an expanded version called a journal storage, or a generalized version, in which nothing is ever overwritten. The way this works is if you have x, the very first time you set x to some value, you end up creating a data structure in cell storage that looks like this. You have a value v1, and you also keep track of the identifier of the action that created that. And it will turn out to be useful for us to know the identifiers of the actions that created any given variable. And how do you get these identifiers? When begin array is called, it returns an ID. Okay, and the system knows that, and this ID is available to the program as well. Then the next version, if x gets set by any action to a different value, what you do is you create that as v2, and you keep track of the identifier that maintains that. And then you got v3, and so on all the way. And the current version, the latest version, might be vn that was written by ID n. Now, if the same action repeatedly writes the same variable, you just create new versions. So it isn't like there's one version per action. It's just that there's one version every time you write something. So literally, nothing is overwritten. And so that's x. So x itself points to the head version, the very latest version that was written. And you could imagine that there are these pointers pulling you back like a linked list. But the nice thing about it is this is the journal store. So x itself is this whole thing. And we'll implement two calls that, when you have, this is basically a memory abstraction. So you need to read and you need to write. So for write, we're going to come up with a call called write journal, which in the notes has, I think, a slightly different name. I think they call it write new value. But write journal makes it clear that it's for journal store. And this is easy. It's some data item x, it's some value v, and it's the ID of the action that's doing the write. And this is very easy to implement. All you do is you create a new version, and then you take the current thing that x is pointing to and make the current version's next pointer point to that, and then you make x point to the new version. So it's just a linked list thing. Okay? And in addition to write journal, we obviously need to implement read journal. And read journal is going to take a data item that you wish to read, x, And for reasons that will become clear in a minute, it also takes the ID of the action that wants to do the read. Okay? So if you want to read something, the idea is going to be the following. The idea is going to be that some of these actions are actions, some of these versions are going to have been written by actions that were committed. Okay? And some of these actions were going to have been written by actions that started writing things and then maybe failed or were aborted. So they never committed. Now, clearly, when you do read journal, you don't want to see the results of those actions that were never committed. Because what you want to see from the definition that we laid out are, once you reach the commit point, you want to see the changes visible. Before that, you don't want anything visible. So as long as you can keep track of which of these actions committed and which of these didn't commit, you can implement read journal by starting at the most recent version and going backward until you find the first version that corresponds to a value that was written by an action that was committed. So what you need to do is start from here and look at IDN. If IDN, you need to maintain another table that tells you whether IDN committed or not. If it committed, then return that value. If not, go back one. And keep going until you find the most recent version that was written by a committed action. If you do that, then read journal clearly returns to you what you would want, which is the value that was written by the last committed action. The only other tweak that you want to do, and the reason why ID is passed as an argument to read journal, is if the current action has already written. So let's say you're implementing an action and you set the value of x to 17. Then when you read the value of x, you would want the value that you set. I mean, you wouldn't want the previous committed action. Now, that's one way of defining read journal. So as you go from the most recent version to the oldest version, you either look to see whether the value that you're reading now is value that you set, your own action set. And if it was, just return that. And it'll return to you the last value that this action set. Otherwise, you keep going until you find the value set by the most recent committed action. And since we aren't dealing here with concurrent actions at all, right? We've already said last time that we're only going to be dealing until next Monday, we're only going to be dealing with one action at a time. There's no concurrent actions. Clearly, this algorithm will be correct. You start from the most recent version, keep going until you find the first version that was either written by this action that's doing the read, or the first version that was written by an action that committed. So clearly, what this means is that you need a table that you have to maintain that stores the status of these different actions. It needs to store which actions committed and which actions didn't commit. And that's going to be done using a data structure called the commit record table. And this is a very simple table. It just has ID 1, ID 2, all the way down to whatever IDs you have. Every time somebody calls begin RA, you return them an ID, and then you create this table that as soon as they create this action, you set their state to pending, which I'll call P. Okay? And anytime an action commits, you replace this P with a C, which is a commit record. Okay? And this thing, once it's replaced with a C for an action, this item is called the commit record for an action. So now when you want to do read journal, and you're looking to see whether for any given action things were committed, the corresponding action was committed or not, you look at this, you see it's ID n, you look for ID n in this table, see if it's committed or not. If it's not committed, then you go to the previous version and you do the same thing. If it's committed, then you return it. Now, it's not actually clear why you need this pending thing here, but it'll turn out that you'll require the pending thing when you deal with isolation on Monday. So for now, you don't have to worry about the fact that these pending things are there. Okay? Now, suppose an action starts and then it aborts. So I mentioned here that when an action starts and it aborts, the system has to do some kind of undoing of data in order for abort to be correctly implemented. So the state of the system is restored to the state before the action even started. The nice thing about this way of implementing version histories and read journal is you don't have to do anything on an abort. If system call, if the application or the system called abort, nothing has to be done, because read journal basically is just scanning this backward, looking for whether the version was written by itself, that same action, or looking for whether the version was written by a committed action. So as long as you can find for any given ID whether it was committed or not, that's all you need. Okay? But just for completeness, and this will become useful the next time, all we'll do when abort is called on an action, so abort takes the ID of the action as an argument. All we'll do is we'll replace, if ID 7 aborts, we'll just replace the pending, we'll replace that with an abort. Okay? So these commit records, this commit record table contains the status of the actions, and that status could either be committed, pending, or aborted. When it starts, it's pending, and then it's pending as long as either it aborts, in which case it's aborted, or it's committed. Now, if it just fails, and you don't do anything about it, and there's no abort call, it'll continue to remain in the pending state. But that's okay, because we're never really going to read the value of anything that's in the pending state, that was set by an action that's in the pending state. So is this clear? Okay, this approach is actually quite reasonable, except that it has a few problems. The first problem it has is, well, it has two related problems, and that's the first class of problems that it has, is that although it looks like we've really nailed this problem of achieving recoverable storage, using this journal storage idea, building general recoverable actions so that for any variable that's written inside here, or read inside a recoverable action, you use this journal storage idea, it's not quite correct, because you have to ask what happens if the system fails while the system is writing this commit record. So the application calls commit, the system's starting to write this commit record, and it fails. Or you might more generally ask, what happens if I create this new version in write journal, and as I'm creating a new version of a variable, the system crashes, so some garbage got written here. Or more likely, some garbage got written not in here, but as I was changing this pointer for x to point to the most recent version, some garbage got written, so all subsequent reads of x don't quite work. The answer to this question is that we know how to solve this problem, because that question is basically identical. Both of these are identical. If we know how to solve the problem of writing a single recoverable sector, a single small item of data, then we know how to solve these two problems, because both of these are, writing recoverably a small amount of data. In one case, a pointer that takes x to point to the most recent version. In another case, it's a single data item that corresponds to the commit record in this commit record table. And so this shows this idea of bootstrap, that in order to build this atomic action, this recoverable action, we end up, and then you bootstrap on, something that we know already how to do, because there are these cases where you have to make sure that the writes to certain pointers and certain table items are done atomically, and we know how to do that because we just told you how to do recoverable sectors. And you could just take shadow objects for these items and implement that to get this bootstrap. So that's the first thing, the first set of problems. There's another problem, not so much a correctness problem, but a problem in general with using these version histories in order to build recoverable actions. Any ideas on what that might be? Like, why wouldn't we want to use this? Disk space? Well, you kind of can't really get around that. I mean, it's true that there are these old versions that you keep forever, but there are optimizations you can bring to bear that sort of delete these old versions that you don't really care about anymore. Because really, the read only requires, at least for the way we laid it out, and we'll modify this when we talk about isolation tomorrow, but really the read here only requires, for a single action case, the last committed version. So you could garbage collect this stuff if you want. Yeah, it's really slow. So for applications where you care about performance or reasonable performance or high performance, this is really slow. And it's not to say that this is a bad idea or an idea that shouldn't be used at all. In fact, it's a perfectly good idea for many cases where you might, for various reasons, want to store historical records of all data, and you don't care about fast read or write performance. So it's perfectly good for certain applications. But it's not good for applications that want reasonably high performance. And the reason this thing is slow is because if you think about it, it actually optimizes what you might think of as the uncommon case. Because what it ensures is that when you fail and you recover, you have to do no work. So crash recovery is really fast in this approach because there's nothing to be done for crash recovery. But reads and writes are slow. Because, I mean, a read involves traversing the list, a write involves doing some, a bunch of pointer manipulations. And so it almost optimizes the opposite of what you would want. If you wanted high performance, you want to follow the principle of optimizing the common case. And in order to optimize the common case, what you want to do here is to make the reads and writes really fast and make maybe pay the penalty of a little bit of extra time in dealing with crash recovery. It's working now? Hello? All right, thanks. Okay. So what you want to do is optimize. Whoa, it's loud. So the integral of the volume over time was correct. Okay. So the solution to this problem, where we want to optimize the common case of reads and writes, but we're okay, taking a bunch of time to do crash recovery, is an idea called logging. So the way to think of a log is it's like a version history, except you don't have a version for each variable. You think of it as an interleaved version of a data structure that interleaves all of the version histories for all of the data that was ever written during all of the actions that ran. So what this means is that you can write the logs sequentially. And you've seen this in yesterday's paper where they used logs for a different application for high performance in a file system, for a system where writes normally would incur a lot of seeks. But you could use the same idea. In this case, we're going to use a log for crash recovery. But the fundamental property of a log data structure is that it needs to be written only sequentially. And we know that disks do that pretty fast. It's only when you have to seek that and read small chunks of data with seeks that you end up being really slow. So we're going to use cell storage to satisfy our reads and writes. So all of those are going to go into cell stores. You're going to read means you just read a variable. You don't traverse any linked lists. And writes, you don't create any new versions. You just write into cell store. But then the log is going to be stored on non-volatile medium, such as a disk, and it's written sequentially. So once we have those two, our plan is going to be as follows. And this plan is the same plan that's adopted in, although there's dozens of ways of doing log-based crash recovery, they all essentially follow the same basic plan. You read and write normally to cell storage, and you also write a copy of what you're reading and writing. You write an encoding of what you're writing, any updates that you make into the log. Okay? And we'll talk in more detail about what you exactly write into the log and when you write into the log. Okay? So that allows us to follow this golden rule of recoverability. It'll turn out that the log is a copy of the data. So you always have two copies of the data, one in cell store, one on the log. So what happens when you fail? Well, when you fail, unlike in the version history case where you could fail and recover, restart, and you don't have to do anything, here, when you fail, the system runs a recovery procedure. And that recovery procedure recovers from the log that we have conveniently arranged to write into non-volatile storage. So it remains even after a crash, and it remains after a crash recovers. And there are two things to do while recovering from the log. For actions that didn't get to finish the commit, for actions that were uncommitted, which is this commit never returned, what we have to do is to look carefully to see whether the corresponding cell store had any updates that were made to it. And it'll turn out that the log is going to help us keep track of what items were updated by any given action. And what we're going to end up doing is for uncommitted actions, we're going to back out. In other words, we're going to undo any changes that it made, and the log is going to help us do that. And conversely, for committed actions, because the semantics we want are that once committed, you would like the changes to be visible to other people. For committed actions, what you would like to do are to make sure that the changes made by all committed actions are, in fact, installed in the cell store. And what this means is that if they turn out to not have been installed, and we're going to use the log to tell us whether they've been installed or not, we will redo those actions. And the second thing we need to do is what happens if an abort is called, either by the application or by the system. Well, in this case, what we have to do is to use the log and to keep track. The log is going to help us keep track of the changes made by this action to the cell store. The cell store itself doesn't have a notion of old or new because it's overwritten, so the log is going to tell us that. And when abort is called, we just want to back out by undoing the changes of the current action. And that's the plan. So first thing we need to figure out is what this log looks like. So as we saw from this discussion, the log is going to be required for us to do two things. We're going to be undoing things from the log, and we're going to be redoing things from the log. So what that suggests is that the log, anytime you update cell store, you change X from 17 to 25, what you would really like to maintain is what the value was before the change was made, so that you can undo if you need to, and what the value is after the change was made, so that you can redo if you have to, if by chance the actual cell store didn't get written at the right time. So really the way to think about logging-based crash recovery is that the log is really the authoritative version of the data. The cell store itself is, you should think of as a cache, and we've seen this idea before. The cell store you should think of as a cache. If a failure happens, you really have to be careful about trusting the cell store, and you don't trust what's in the cell store. You start with the log, and you, by selectively undoing certain changes that were made and redoing certain changes, you produce a more pristine, correct version of the data, which corresponds to the changes made by all the committed actions being visible and the changes made by all the uncommitted actions being wiped away to the previous version. Okay, so what does the log look like? Well, as I've already said, a log is like a version history, except it interleaves everything and it's sequential. So it's really an append-only data structure. And there's a few different kinds of records that a log maintains, and in particular, two are going to be interesting to us. So there are two types of records that we care about. The first type are update records, which are written to the log whenever a cell store item changes. So if X goes from 17 to 25, what you would write is an update record that looks like this. You store the ID of the transaction, ID of the recoverable action that did the update, and then you store two items. One of them is an undo item, or an undo action, actually, and an undo action that might say, and a redo action So what this means here is that, let's say that the actual step of this action said x is assigned to some value nu. In the log, what you would write is keep track of the old value, the current value of x, and make that the undo step. And then keep track of the change that was made and make that the redo step. So now, after doing this, if the system were to fail and this action 172 were to never commit, then you can systematically start with the log, start with the latest item in the log, and go backward and undo any changes made by actions that didn't commit. And conversely, and you might need to do this as well, you might want to look at all the actions that committed and make sure that all those actions, those individual steps in those actions are redone, so that once the crash recovers, you have the correct version of the data. Now, the other thing that you will need, and you'll see why in a moment, is another kind of a record in a log, which we're going to call the outcome record. And this outcome is the thing that keeps track of whether an action committed or not, right? Remember I said you're going to look through the log and figure out which actions committed and which didn't commit. You need to store that somewhere. In particular, what that means is that when an action commits, you better make sure that there is an item in the log, because the log really is the only correct version of the data. So you have an outcome record, and this has an ID of the action. It might be 174, and there's a status that might say committed. And other values for the status might be aborted, is another possible value of the status. Another is pending. So when, for various reasons, what we will have is when begin recoverable action returns with an ID, we will create a log entry that says that this action has begun. So we might have a begin record. It's not that important to worry about for now. But the status of a committed record and an aborted and the update type are important to understand. So once you have this log structure understood, the log data structure understood, what you have to think about are, there are two questions that you end up spending a lot of time thinking about in designing these log-based protocols. The first one is when to write the log. And the second one is, I sort of said, oh, you just look through the log and undo the guys who didn't commit and redo the people who committed. But you have to be very careful about doing that, and that corresponds to this question of exactly how to recover. How to systematically recover, so the state of the system is as I have described before. So those are the questions we're going to deal with in the next few minutes. Let's do this with a specific example, and it'll turn out the answer doesn't really depend on the example, but the example is good to give you the right intuition. And this example is actually a pretty common example of a disk-bound database. So a disk-bound database is one where you have applications writing to a database, which is where the cell storage is implemented, and this cell storage is on disk. So you might have writes of cell items X, and they go to a database. And similarly, in any disk-bound database that you want crash recovery for, you need to maintain a log. And for various reasons, having to do primarily with dealing with failures of the disk hardware itself, it's very often useful to and expedient to maintain the log on a different disk. So we'll maintain, for this example, the log on a different disk. So whenever write X is done, just looking at the log structure, the log data structure, you need to write an update record and append that to the log. So at some point, you will need to write this to the log. You need to log the update. That says that X changed from something to something else. So the question is, when do you write both of these? So one approach might be that it really doesn't matter. As long as the log gets the data, you're fine. But that has a couple of problems. In particular, suppose you write X without writing the log entry. And as soon as you write X, before you have a chance to write to the log, you crash. Or the system causes this program to abort. Or the program itself, aborts, right? So it writes X, and then it does some calculation, and then it decides to abort. Now you're in trouble because the log hasn't kept track yet. The log hasn't had a chance of keeping track of what the old value was. Which means that if you really want to restore this database by undoing this write to X, you have to do a whole lot of work, and it might be impossible to do it. If you didn't know, for example, what the current value was, there is absolutely no way for you to restore to the old value. So what this suggests is that you better not write to the cell store before you write to the log. Because if you wrote to the cell store before log write, and the system crashed right after, or failed or aborted, you won't really have a way, in general, of reverting to the version of the data item before this write. And you do need to revert because it just aborted or failed, so you need to back out of all changes that were made. So that suggests the first part of our protocol, which we're going to call the wall protocol. Actually, that is the wall. I mean, this is not the first part. This suggests this wall protocol. Wall stands for write-ahead logging. The protocol says, update the log or append to the log before you write to the cell store. That's what it says. Write-ahead log says, write the log before you write the cell store. The advantage of writing the log before you write to the cell store is that suppose now you wrote, you set X to some value, and then you crashed, then you're guaranteed that if the cell store got written, the log got written, which means that if this action didn't commit, you can go through the log and undo that action because you know that the log entry got written correctly before the cell store got written. And if the log entry didn't get written, then you know the cell store didn't get written, which means you don't have to undo anything for that particular data item. So either way, you're fine. Well, there's another part to this protocol that we're going to need to meet the semantics of a recoverable action that we wanted, which is that once you reach commit, you want the changes made by that action to be visible to all of the other people, all of the other actions that are subsequent actions. And what that means is that before you return from the commit, you better make sure that the commit record for this action is logged to the disk, is logged. Because if you didn't do that, and you just returned, then you can't be guaranteed that all of the writes that were done to the cell item were actually put onto the cell store. There's no guarantee that these writes to the cell store actually got written to the cell store. Because all you are doing in this protocol is ensuring that the writes to the log are being written before the writes to the data. Nobody's saying when the writes of the cell store really are happening and finishing. Which means if the action commits, you better have, and you return committed to the user, to the application, then you better have a way of making sure that if a failure now happened, the system, when it recovers, knows that this action committed. Which means, it follows then that if you want those semantics, that you better write the commit record, the fact that this action committed, to the log before the commit returns. And really the only reason you need that is that we've decided that we wanted the semantics that if an action commits, you want the results to be visible to everybody else. Later on, we'll see that this is related to this notion of durability. So write commit record before returning from commit. So two main ideas. Write-ahead logging means make sure you write to the log, append to the log before you write to the cell store. And in order to make sure that committed actions, the results of committed actions are visible even after failure to subsequent actions, log the commit record before you return from the commit. So now we're actually in good shape to specify this recovery procedure that I've alluded to before, because the log is going to contain these update records and these outcome records. And that's going to allow us to decide what to do upon crash recovery. And actually, the only other piece we need is to decide what happens on an abort. And that's actually pretty straightforward. If the system calls abort or if a user application calls abort on an action, what abort has to do is to look through the log. Remember that all of the writes have been written. Anytime a write happens, you ensure you don't actually care about when the write actually happens to the cell store. What you care about is that the write happens to the log before the write happens to the cell store. So if an abort were called, all you have to do is to ensure that before abort returns, all of the actions done by this, all of the steps taken by this action are undone, and the corresponding cell values are undone. Okay? And that's all you have to do when you implement abort. So from this discussion is actually going to be one thing that I haven't really specified very clearly is when the actual writes happen to the disk or to any cell store. And it turns out that it really doesn't matter. If there's no failure, as long as you ensure, you could have caches in the middle, you could have anything else. As long as you ensure that if there's no concurrency, we'll deal with that next time. But as long as you ensure that when you have actions that come one after the other that are recoverable, that the values that are read are only the values that were written by previously committed actions, then it really doesn't matter when those were actually written to the disk. But for crash recovery to work, the main thing that matters is to make sure that the log keeps track exactly of all of the things to undo for uncommitted actions, and for things that got committed, to make sure that the log keeps track of the commit record before the commit returns. So given the story, the way the recovery procedure works is the following. The first step is the system fails and then it recovers. You scan the log backwards. And as you're scanning the log backwards, you keep track of two kinds of actions. You keep track of actions that were either committed or that were aborted. Okay? And what that means is that for actions that were committed or aborted, the cell store for those actions is in a certain state, or needs to be in a certain state. For committed actions, it needs to be in a state that's the result of finishing the committed action. And for the aborted actions, what it means is that when abort returned and there was an aborted action, abort already undid the state of the cell store by the definition of the abort procedure. So what that means is for log records that contain the type outcome and the status aborted, you don't have to do anything because the changes were already undone before that aborted record was written. So what you do in scanning the log backwards is you build up two kinds of actions. You build up winners, which are actions that were committed or aborted. And you build up a list of losers that were none of these. In other words, they were pending actions that kind of just, during a failure, they were pending, so they didn't commit, and they were never aborted. And so the plan now is to make sure that the cell store is correctly restored to the state that it was before the crash, where all of the committed actions results are visible, and none of the uncommitted actions results are, all of those are blown away. All you have to do is to redo the winners that were committed. You don't have to do anything for the aborted winners because they were already undone. So you have to redo committed winners. And you have to undo any changes made by losers. Right? Because these losers, by definition, were things that didn't commit or didn't abort. And the reason you only redo the committed winners rather than all winners is it makes no sense to redo aborted winners. And you don't need to undo them because they were already undone when the abort record was written to the log. So this is the basic idea for dealing with one of these databases, but there's 5 or 6 optimizations that end up making this kind of system go faster. You'll see some of these optimizations buried inside the System R paper, which is the discussion for tomorrow. But what I'll do on Monday is spend 5 minutes talking about the most important optimizations. And then I think the whole story will become clear. So the plan for the subsequent lectures on this topic are, on Monday we'll deal with isolation, and on Wednesday we'll continue to talk about isolation and then talk about different issue, consistency.